now, actually, the rotation axis is very close to the direction of us, the direction of Earth and the Sun, and also the anti-tail, this jet that is pointed towards the Sun that we saw wobbling, is now almost pointed at us.
On January 22, 2026, the sky aligned in a way astronomers had circled for months, with Earth set perfectly between the Sun and 3I Atlas. The headlines called it an interstellar comet, familiar and safe, yet behind the scenes. Quantum AI rechecked the path and found patterns that chance could not defend. Instead of noisy chaos, the trajectory showed calm structure, timed angles, and stability across billions of miles. Numbers replaced guesses, and the results felt godlike rather than random. To understand why machines were needed to see this, we must return to the moment 3I Atlas first appeared. What was missed when it looked ordinary? At first, 3I Atlas did not arrive with drama, warnings, or headlines because on July 1, 2025, it appeared as nothing more than a fast-moving point of light on a screen in Chile. The Atlas Survey telescope flagged it automatically, just like thousands of other objects that pass through the system every year, and no one rushed to the microphones or cleared schedules to study it. Early data suggested a familiar story. The object was classified as only the third known interstellar visitor, following Oumuamua and Borisov, which made it interesting but not alarming. Astronomers had already adjusted to the idea that interstellar objects exist, so another one felt less like a shock and more like a footnote in a growing list. For the public, there was no reason to care, because nothing about Atlas seemed urgent or threatening. During those first weeks, the narrative stayed calm. There were no emergency meetings, no sudden telescope takeovers, and no reason for major observatories to interrupt planned research. The object appeared to be passing through, following a path that looked acceptable under standard models, and the system continued to watch quietly in the background. Then something subtle began to change. By late summer, more researchers started pulling the same data, not because they sensed danger, but because the numbers refused to settle into a clean explanation. Small inconsistencies appeared in speed, angle, and timing, not large enough to cause panic, yet persistent enough to raise eyebrows. Each attempt to smooth the path introduced new questions, and the math stopped behaving the way experience expected it to. By September, nearly 70 research papers were circulating across the community. That number alone was unusual for an object that was supposed to be routine, because scientists do not argue this much about something truly simple. Some teams defended the ordinary comet explanation, while others admitted the motion felt strained inside existing frameworks. What had begun as quiet observation slowly turned into open disagreement. The shift was not driven by where Atlas came from, but by how it moved once it was found. Its behavior did not scream danger, yet it also refused to fade into statistical noise, which placed it in an uncomfortable middle ground. This was the moment when curiosity replaced comfort and when traditional tools started to feel insufficient. As confidence in the old models weakened, a new question emerged across research circles. If standard methods could not explain a simple passing object, what would happen if the analysis itself changed? That question opened the door to a different approach, and it pointed directly toward the role quantum AI was about to play. But before machines could reveal what humans missed, one problem had to be faced. What exactly was wrong with the trajectory everyone thought they understood? The real problem with Atlas did not appear in its size or brightness, but in the path it carved through the solar system. From the moment astronomers tried to map its motion using traditional models, the equations refused to settle, even when the input data was cleaned and rechecked. This was not a case of missing information, but a deeper mismatch between expectation and reality. Most interstellar objects follow chaotic paths shaped by random encounters and uneven forces. Their trajectories tend to cut across planetary planes at sharp angles, reflecting the messy structure of the Milky Way. Atlas did the opposite. It moved on a retrograde path, yet stayed surprisingly close to the orbital plane of the planets, a region shaped by long-term stability rather than chance. The numbers made the situation uncomfortable. Calculations showed that the probability of an interstellar object aligning this closely with the planetary plane by accident was around 0.2%. In statistics, this is not impossible, but it is rare enough to demand caution instead of comfort. When something falls this far outside expectation, science does not ignore it. The contrast became clearer when astronomers compared scales. The disk of the Milky Way is tilted by roughly 60 degrees relative to the solar system. An object traveling freely through that structure should arrive from almost any direction, yet Atlas slipped in nearly level, as if the solar system had been waiting for it. Each new simulation confirmed the same result, even when assumptions were changed. Attempts to explain the motion with gravity alone introduced new contradictions. Minor adjustments solved one inconsistency while creating another, which suggested the issue was not noise but structure. The path appeared smooth, measured, and resistant to disruption, qualities rarely associated with interstellar visitors. This growing tension exposed the limits of older tools. Classical models rely on simplifying assumptions, and they work well when systems behave as expected. Here, those shortcuts collapsed. The trajectory was not wild enough to dismiss and not simple enough to resolve. That was the moment when researchers began to reconsider the method itself. Instead of forcing Atlas into pre-built categories, they asked what would happen if the data was allowed to speak without guidance. This shift did not begin with conclusions, but with humility. Quantum A. I entered the analysis not as a final answer, but as a way to explore every possible path at once. Millions of orbital scenarios could be tested in parallel, without preference or bias. The goal was not to prove intent, but to understand why the motion felt so controlled. As the results began to emerge, one conclusion became unavoidable. The problem was not that the trajectory was unknown, it was that it was too precise to be ignored. If the old models failed because the path was not random, what pattern would appear once chaos was no longer assumed? That question leads directly to what quantum AI revealed next. Quantum AI entered the analysis. The story of Atlas changed from confusion to clarity, because the data was finally allowed to speak without human shortcuts. Instead of testing one solution at a time, the system explored millions of orbital paths in parallel, comparing long-term stability, timing, and alignment across the entire solar system. What emerged was not noise. The simulations showed a trajectory that stayed calm over time, resisting the kind of drift expected from an object that had traveled through deep interstellar space. While most visitors pick up randomness from countless encounters, Atlas followed a path that remained coherent, as if it had been preserved rather than battered. This stability was not brief. Quantum A. I tracked the motion backward and forward across billions of miles, and the results remained consistent even when variables were adjusted. Small changes in mass or speed did not collapse the solution, which suggested the trajectory was not fragile. In physics, stability usually appears when a system has constraints, not when it is left to chance. The most striking result was directional focus. Instead of drifting through empty space, the path seemed to brush past key regions of the solar system where gravity, visibility, and energy exchange are strongest. This did not imply a destination, but it did imply awareness of structure. Random motion tends to ignore landmarks, yet this motion respects them. As the AI refined its output, a term began appearing in internal summaries. The trajectory was labeled as low entropy. In simple terms, this means the motion was ordered rather than scattered, and predictable rather than wild. For an interstellar object, that classification is rare. Importantly, the system did not assign purpose. Quantum AI does not think in motives or intentions. It only measures patterns and probabilities, and here the probabilities leaned away from coincidence. The model did not claim design, but it did rule out chaos as a satisfying explanation. Human researchers reviewed the results with caution. They checked for bias, reran the analysis, and challenged the assumptions built into the system. Each time, the same geometry emerged, calm and repeatable. The more they tried to break it, the stronger it appeared. This forced a quiet shift in tone. Atlas was no longer discussed as a wandering object that happened to pass by. For an interstellar object, that classification is rare. Importantly, the system did not assign purpose. Quantum AI does not think in motives or intentions. It only measures patterns and probabilities, and here the probabilities leaned away from coincidence. The model did not claim design, but it did rule out chaos as a satisfying explanation. Human researchers reviewed the results with caution. They checked for bias, reran the analysis, and challenged the assumptions built into the system. Each time, the same geometry emerged, calm and repeatable. The more they tried to break it, the stronger it appeared. This forced a quiet shift in tone. Atlas was no longer discussed as a wandering object that happened to pass by. It began to feel like something that moved with rules of its own, even if those rules were not yet understood. The question was no longer where it came from, but why its motion refused to behave like chance. If the path itself showed order, then the physical object had to be examined more closely. What kind of body could maintain such structure while crossing the galaxy? That question points directly to what telescopes like Hubble and James Webb would soon reveal. Was no longer discussed as a wandering object that happened to pass by. It began to feel like something that moved with rules of its own, even if those rules were not yet understood. The question was no longer where it came from, but why its motion refused to behave like chance. If the path itself showed order, then the physical object had to be examined more closely. What kind of body could maintain such structure while crossing the galaxy? That question points directly to what telescopes like Hubble and James Webb would soon reveal. The moment Hubble turned its attention toward Atlas, the object stopped fitting into any familiar box, because the data refused to behave like a normal comet story. Securing time on the Hubble Space Telescope is rare, yet this visitor triggered a target of opportunity, which meant other observations were paused so scientists could look closer. That decision alone suggested quiet concern rather than casual curiosity. The first surprise came from size estimates. Hubble measurements placed the nucleus somewhere between roughly 300 meters and more than 5 kilometers wide. A range so wide it challenged confidence. In astronomy, uncertainty is normal. But margins this large usually signal unstable light behavior rather than poor instruments. Instead of reflecting light from a solid, predictable surface, Atlas appeared to scatter it in ways that changed from one observation to the next. Then the James Webb Space Telescope added another layer. Using infrared spectroscopy, Webb examined the chemical fingerprint and found something that broke expectations. Nearly 87% of the detected gas was carbon dioxide, while water was almost absent. Classical comet models rely on water ice as a primary driver of activity, so this composition forced researchers to pause. If water was missing, then the usual explanations for jets, tails, and brightness no longer applied cleanly. Surface behavior made the situation even stranger. The way Atlas reflected sunlight did not match known patterns for rock, dust, or ice. Instead of smooth predictability, the reflections hinted at complexity, as if the surface was layered or shifting. This did not mean artificial, but it did mean unfamiliar. As more data arrived, confidence in standard categories continued to erode. Astronomers could no longer describe the object using a single label without adding exceptions. Each attempt to simplify the description removed clarity instead of improving it. What once looked like a passing body now felt like a system with internal rules that resisted shortcuts. Importantly, none of this proved intent or design. Science remained careful, because unusual does not automatically mean extraordinary. Yet the accumulation of mismatches created pressure. When size could not be pinned down, chemistry contradicted models, and surface behavior stayed inconsistent, coincidence became harder to defend as the full explanation. This growing discomfort pushed the conversation forward. If Atlas did not behave like a typical comet, then its activity had to be examined more closely. Attention shifted from what it was made of to how it released energy into space. That focus led directly to the most controversial observation so far. Something was pointing toward the sun, not away from it, and it refused to disappear with time. If gravity and chemistry could not fully explain this behavior, then what mechanism was shaping it? That question opens the door to the strange geometry revealed by the jet itself. The moment astronomers confirmed the presence of an anti-tail on Atlas, the conversation shifted from curiosity to disbelief, because this was not how comet physics was supposed to work. Every textbook example shows material pushed away from the sun by radiation pressure, yet this structure pointed directly toward it and stayed there. At first, the explanation sounded simple. Some researchers suggested dust fragments or unusual grain behavior, arguing that sunlight could briefly sculpt strange shapes under rare conditions. That argument weakened as weeks passed and the feature refused to fade. A temporary illusion should collapse quickly, but this jet remained sharp, narrow, and persistent across multiple observation windows. What made the situation more troubling was its motion. High-resolution imaging revealed that the sunward jet was not static. It wobbled with a regular rhythm, completing a cycle roughly every 16 hours. Random dust does not keep time. When patterns repeat with this level of consistency, physics usually points to rotation or internal structure rather than coincidence. Then Hubble captured something that pushed the debate further. Instead of one jet, 3 distinct mini-jets were observed emerging from the nucleus. They were not scattered or uneven. They were separated by exactly 120 degrees, forming a perfect triangular symmetry around the object. This geometry did not appear once and vanish. It held steady across repeated observations. Symmetry is rare in uncontrolled natural systems. In chaotic environments, irregularity dominates because small disturbances grow over time. Here, the opposite happened. The configuration resisted distortion as if the system corrected itself. That behavior did not fit comfortably within standard comet models. Quantum AI was brought back into the discussion, this time to analyze shape and repetition rather than motion alone. When the system evaluated the jet arrangement, it flagged the symmetry as statistically unusual. The chance of 3 independent jets maintaining equal separation over time fell well below comfortable thresholds. Once again, probability leaned away from randomness. Importantly, this did not prove a mechanism. The AI did not label the jets as engines or tools. It simply recognized the order where disorder was expected. That distinction mattered, because science relies on ruling out what something is not before guessing what it might be. As data accumulated, language across research notes became cautious but uneasy. Words like odd and unexpected appeared more often than normal. The anti-tail was no longer treated as a visual trick. It was treated as a feature that demanded explanation. The tension grew because this geometry appeared at a critical time. Atlas was approaching regions of stronger gravitational influence where instability should increase rather than decrease. Yet the jets remained aligned, balanced, and timed. That contradiction forced a pause. If these structures were driven purely by sunlight and chemistry, then they should respond violently to changing conditions. They did not. Instead, they behaved as if governed by rules that stayed consistent under stress. This left researchers with a narrowing set of options. Either nature was producing a configuration rarely seen before, or existing models were missing something fundamental about how this object released energy. As attention turned from geometry to power, a new mystery began to glow, one that could not be explained by shape alone. If the jets were not random, then what energy source was feeding them? The mystery deepened when scientists stopped looking at how Atlas moved and began focusing on how it interacted with light. What they found did not match the behavior of any comet, asteroid, or interstellar object studied before. Polarimetry data revealed something unsettling. The way Atlas scattered sunlight showed a deep and narrow negative polarization pattern, a signal that points to extreme surface uniformity. In simple terms, the light bounced off the object in a highly ordered way rather than spreading randomly. This type of response is rare in natural space debris because rough surfaces usually break light apart instead of guiding it. The chemical picture only added to the confusion. Observations detected an unusually high release of cyanide molecules measured in the billions per second, which placed Atlas among the most cyanide-rich objects ever recorded. At the same time, carbon chain compounds were almost completely missing. This imbalance mattered because those chains are normally responsible for many visible comet effects. Then came the green glow. Amateur astronomers in the southern hemisphere captured images of Atlas shining with a vivid emerald color, a sight usually linked to diatomic carbon emissions. The problem was simple and serious. The object did not contain enough of the required carbon to produce that light through known reactions. At this point, traditional chemistry began to fail. If the glow could not be explained by expected compounds, then either the measurements were wrong or something else was energizing the surrounding material. Repeated checks confirmed the data. The glow was real, and the chemistry did not support it. Quantum A. I was once again used to explore alternatives. The system compared the observed emissions with known chemical and physical processes, ruling out standard reactions one by one. What remained was a narrow set of possibilities tied to ionization, rather than combustion or sublimation. Ionization does not require large amounts of material. It requires energy. This shift changed the question entirely. Instead of asking what Atlas was made of, researchers had to ask what was feeding energy into its environment. Sunlight alone struggled to explain the intensity and stability of the glow, especially given the object's unusual composition. The implications were uncomfortable. Energy fields are not commonly associated with small interstellar bodies, and when they do appear, they tend to fluctuate wildly. Here, the glow persisted. It did not flicker or fade as conditions changed. Once again, no claim of technology could be made. Science stays grounded because extraordinary conclusions demand extraordinary evidence. Yet the pattern repeated itself. Movement showed order. Geometry showed symmetry. Now light itself showed discipline instead of chaos. Each layer removed another piece of comfort. Atlas was not only moving differently, it was reflecting and emitting energy in ways that refused to fit existing frameworks. As alignment peaked and attention shifted outward, a final question began circulating quietly. If light and chemistry pointed to an internal energy process, what else might be escaping detection? That question would soon collide with a signal no one expected, and the story would move beyond telescopes into silence. The story took a darker turn when attention moved beyond telescopes and into silence, because this was the moment information stopped flowing freely. As alignment peaked, reports began circulating within the radio astronomy community about an unusual signal detected near 1,420 MHz. For decades, this frequency has carried special meaning. It marks the hydrogen line, a natural marker shared across the universe, and it sits at the center of the range where SETI has listened for signs of intelligence for more than 50 years. Signals at this frequency are rare, and structured patterns are even rarer. According to early leaks, the detected burst was not a random spike. Its structure appeared ordered, repeating, and timed, which immediately raised alarms among those who understood the implications. Yet before details could spread, official responses arrived quickly and quietly. NASA described the event as terrestrial interference. The explanation suggested reflections from satellites or background noise bouncing through the comet's surrounding material. On paper, this sounded reasonable because space is full of interference. In practice, the lack of released raw data made the explanation difficult to test. Requests for clarification were met with restraint. When a Freedom of Information request was filed for related radar and signal records, the response avoided confirmation or denial. Instead, the language pointed to national security, a phrase rarely associated with small interstellar objects. That choice of words shifted the tone. Scientists are used to delaying data, but classification introduces a different weight. It signals concern not just about accuracy, but about impact. At this stage, the issue was no longer limited to astronomy. Quantum AI was again applied, this time to contextual patterns rather than direct measurements. The system compared the reported signal location with historical anomalies, including known listening zones and previous unexplained detections. One alignment stood out. The incoming vector of Atlas fell within a narrow angular range of past signals that had never been fully resolved. On its own, this meant nothing. Coincidences happen, especially when large datasets are involved. What made it uncomfortable was repetition. Once again, probability stacked toward the unlikely. The scientific community did not panic. Publicly, discussions remained careful, measured, and incomplete. Privately, however, the silence grew louder. Emails slowed, briefings narrowed. The usual openness that defines global research began to tighten. No proof of intent emerged. No confirmed message was announced. But the pattern repeated a familiar theme from earlier observations. When something challenged expectations without breaking known laws, access narrowed instead of expanded. This created a divide between what could be discussed and what could not. The absence of data became part of the story, because gaps invite interpretation. In science, silence can be as meaningful as noise. As Atlas continued its path toward the outer regions of the solar system, time became the final pressure. Soon, distance would limit observation and opportunities would close. If nothing unusual was happening, transparency would cost little. If something was, then delay made sense. That tension remains unresolved, and it leads to a question that refuses to fade. As this object moves closer to Jupiter and out of reach, are we running out of time to understand it, or are we being protected from understanding it too soon? Atlas will leave the solar system in 2026, and with it goes a rare chance to observe something that refuses easy answers. Quantum AI did not confirm intelligence, yet it also refused to label this event as random. Old models broke, new tools revealed order, and the data raised questions that science is still not ready to close. Maybe this was not a message, but a test of how we react when certainty disappears. If patterns begin to look more like design than accident, what does that say about us as observers? Share your thoughts, because this story does not end when the object fades from view.